Alright, now, final part of this set of the videos. I know the periodicity part is a little long, but now we're going to talk about the periodic trends. And again, for each of these topics that we sort of talk about, you want to see how can I apply it to the overall big picture of this unit. It's not just how does it apply to just the specific topic. We're going to start to branch, and you're going to see more and more of the information as we go. So let's jump into it. The main three trends that we're going to talk about right now are ionization energy, electron affinity, and atomic radius. You may be saying, but we learned about at least one more last year, and it wasn't electron affinity, it was electronegativity. We're going to talk about electronegativity a little bit later as we go into bonding, so that's going to be a part of big idea 2 a little bit more. But ionization energy, as we talked about before, is the energy required to remove an electron from a gaseous atom or ion. So if we're looking at what we have here for magnesium, as we lose that electron or pull that first electron off, it takes 735 kilojoules per mole. As we continue, notice the jump. As we try to take off that second electron, it takes a little bit more energy in order to have this happen. Remember while we were talking about our reactions and what's actually happening there with forming the ions and different things like that. When we have magnesium, say for magnesium oxide that's being formed, there's 735 plus 1,445 kilojoules of energy that are needed just to be able to separate those electrons from the magnesium atom. And that's where things are it's gonna be its most stable. Now, note here, notice that we went from 1,445 to, man, we made a huge jump to 7,730. Why would that be a problem? Well, now we've gotten past those two that were on the valence shell, and now we're to what we call the core or kernel electrons. These are going to be held a lot tighter to the nucleus. They're not being shielded as much, and so they're actually going to have a higher effect or a tighter pull on those electrons. Now, can we separate that third electron? Yes, but it's going to take a tremendous amount of energy, and so this is one of the reasons why you rarely see this happen in a regular chemical reaction. Now, in general, as we go across the period from left to right, we see that the first ionization energy increases. Notice I specified the first ionization energy increases. We can continue to try to move electrons, and each time the energy demand is actually going to go up. Now, why is this? Electrons added in the same principal energy level do not completely shield the increasing nuclear charge caused by other protons, or the added protons. What this simply means is, as I continue to add protons to the nucleus, it's going to start to affect the attraction that we're going to have between the protons in the nucleus and the electrons around it. Now, electrons in the same principal energy level are generally more strongly bound from left to right because we're increasing in atomic number. Now, as we go from top to bottom, we notice that it decreases. Well, why? The electrons are being removed are on average farther from the nucleus. Each row that we go down, each period, it's further and further away. Our radius gets larger, so the further it is from the nucleus, the easier it is to just pull it right off. This is what we're looking at here. Note the difference of what we have for our magnesium atom. Once we pull one electron off, notice how much we actually dropped in terms of our total size. Why do you think that we have that total drop? It goes back to what we just discussed, okay? Now, going even further, note what we're seeing here, that we take off that second electron and we have an even larger drastic drop. This is what I want to start getting you to think about as we talk about it. And I want you to actually try in your notes or somewhere on your paper in the summary section to answer this question. Explain why the volumes change in terms of electrostatics, in terms of the interaction between the charges between them. As we look at ionization energy, as a trend, if we were to graph everything going from period 1, starting with hydrogen, all the way down, note what happens to our ionization energy. A lot of people would think that it would be a steady decline or something like that. But note that as we go through, from here, from helium, lithium starts here and increases till the point where we get to neon and it's at a high point. Sodium again starting at the bottom, then it goes up. Note which elements it is that are at the top of each of these peaks. Why do you think that is? What would cause that problem? Also notice the pattern that we're seeing as we go from helium all the way down to radon, our last noble gas. Notice how we have this steady decline. Why would that be? That's going back to those previous slides that we just talked about, okay? Now, I want you to note what we're seeing here. For sodium, we know that it usually has a +1 charge, or it only usually loses one valence electron. Let's take a look at what's happening here. Our ionization energy here, 495 kilojoules per mole, very low. And then all of a sudden we jump, once we lose that one, once that one has been taken away, we jump to over 4,000 kilojoules of energy. That's a big jump. Again, magnesium, looking at the same thing, 1445, then it jumps to over 7,000. Again, aluminum, notice each time we're increasing, and then the further we get over, the larger the change in energy needed just to take away that valence electron, to the point where we get here and there really is no taking away. You can't take away. It's too high in energy. This is what we're describing as we talk about that shift or that general trend that it increases from left to right. Okay? Now, explain to me, why does the graph of ionization energy versus atomic rho, why is it not linear? What are the exceptions? So for that one, you actually can use your textbook. The graph that I presented to you on the slide is actually a part of your textbook in chapter 7. All this information is coming from chapter 7. The next trend that we're going to talk about is electron affinity. Now, the electron affinity is letting us know the energy change when we add an electron to a gaseous atom. Notice that we're looking at adding the electron to the atom, making it negative. So where do you think the strongest concentration, or the highest area where we're going to find these that are going to gain or change energy, from this? This is where we're looking at our nonmetals mostly. We're going to look at the trend across the entire periodic table, but the one that will be associated with this the most will be our nonmetals. Now, in general, as we go from left to right, we're going to see that the values become more negative, or that the process is going to be more exothermic, or lose more energy to become more stable as we get closer and closer to our noble gases. This is what, again, made them so noble, made them desired to be like. Everybody wants to have that lower energy. Now, as we go down the group, get closer and closer to the metals, it becomes more positive, meaning that as we try to add, it's actually going to gain or increase in energy. And we don't want that. Usually we want to go the opposite way. We want to lose energy to get that stability. Atomic radius we've dealt with before. As we go from left to right, it's going to decrease because the effective nuclear charge is going to increase, meaning we're going to get more protons and whatever in towards the center, into the nucleus. This is actually going to draw the electrons that are further away in closer. There's going to be more of a pull, more of a charge against it. As we go down the group, it's actually going to increase because that's where we're going to add each principal quantum energy level. Okay? Now, this is giving us a general idea of what we're observing when we deal with our atomic radius. So cesium, francium, somewhere around those are usually going to be the larger variety. Whereas as we go to helium, very, very small, the electrons are pulled very, very tight to the nucleus. This is where we're going to end our show for now. If you have any questions, please come and see me. Write them down so we can answer them in class, because if you have the question, there's most likely someone else who has it as well. I know it's a lot of information. We basically just covered an entire chapter in probably less than 30 minutes. So Please take the time, sort of let it marinate a little bit, and then come into class ready to go. I will see you all later. Have a great and wonderful day.